So we left off in 3.1, having gotten to this page where it says right at the top, let's check that with Maple. And so we know that we can turn this system of differential equations into an entry in Maple. And we're going to do more than just check the D-solve. We're actually going to play around on Maple as a nice little review. And so switching over to Maple, you can see that there's a lot of things that we can do. Remember, the with linear algebra, that's new for us in this section if we want to do anything with matrices. But we can get a sense of how a system of differential equations, like the one that we're looking at, behaves by looking at its phase portrait. And remember, the phase portrait is the phase plane. Oh, it doesn't like this. I forgot to hit enter. Silly me. There we go. It doesn't like this because I forgot to hit enter again. And any second now, Maple. There we go. We can see a phase plane. Remember, that's just giving us kind of the direction field, not the vector field, just the directions. But by adding initial conditions, we can kind of get a sense of what any solution curve would look like on the phase plane. And so we can also visualize our system using a vector field if we want to know not just what direction are things going, but how quickly are the solution curves moving. And so this graph, this is our vector field, allows us to see that the further you are from the origin, further out here, or out here, or out here, or out here, the further you are from the origin, the longer those vectors are, which means the solution curves are moving faster. So this looks an awful lot like that, but with the addition of having the vectors have actual length, and the length corresponds to the magnitude of the slope at that point, how strong those particular solutions are moving at that particular location. And of course, we can take a look at what's going on if we kind of zoom in 3 dimensions. We can kind of see what's going on. As I rotate this, we can see the phase plane, or what is basically the phase plane, without the t-axis. But when I rotate it and I actually see what happens with time, you can see that the x, or in this case the y curves, as time goes by, t equals 0 goes like this. You can see that the y-axis seems to be, all these solution curves seem to be kind of zeroing in on y equals 0. So it looks like all of our solution curves, their y-coordinates head towards 0. But if we want to see the x-coordinates, we kind of have to head in this direction. And you see that, oh, it's a little bit more complicated, the story, when we're talking about the x-coordinates. Some of them, when we start, the x-coordinates get smaller, and then they take off and get bigger. Some of them, they start off in a particular location, and they just head across, and they go like this, and they go from being positive to being negative. But it looks like nothing's headed towards 0 for the x-coordinate. And that makes sense given what we've seen on the phase plane. That a solution curve, that if we started here, the x-coordinate would just slowly get bigger and bigger and bigger, more positive, while the y-coordinate gets close to 0. Over here, the x-coordinate gets a little bit more positive, and then it goes really negative as the y-coordinate heads towards 0. So we know how to make sense of a phase plane, a vector field, even a 3-dimensional phase plot, right? To be able to see what's going on there. They let us see what's going on in multiple ways. And of course, we can just solve the system with D-solve. And that's going to give us something, well, predictable, something like what we would imagine. Maple says, oh, the solution for that? Well, that looks like this. And we could have found that because this is a decoupled equation. That y of t equation is decoupled. That means the system is partially decoupled, which is totally solvable, and we would have wound up with the exact same answer. So we can solve it analytically because it's partially decoupled. But Maple allows us to solve things even if they're not. So in Chapter 3, what we're going to do is turn that system of equations into a single coefficient matrix. And from that single coefficient matrix, rewrite a matrix equation and know that all the information that's encoded in that coefficient matrix All that information, just those 4 numbers, that's all that's required to be able to explain what's going on the phase plane. So that's a big deal for us. So if we flip back to the notes, that kind of is the long way around to being able to verify that we can get that solution. So the second example, and this is kind of the last little bit for this section, is kind of going back to an old pal of ours, which was the undamped harmonic oscillator. And this one in particular, if you recall, we made it so that K was equal to, or sorry, K over M was equal to 1. And that allowed us to come up with this second equation, the dV dt equation. And it turns out if you rewrite this in matrix form, you have the matrix form looks like this, where that y of t is just some kind of, not of t, just y. Doop, doop, doop. Just that y is equal to the matrix y v. So that, if you substitute it in here, will give you your system of equations on the right-hand side. And if you substitute it over here, that'll give you dy dt and dv dt. Right? So suppose we know that these two things right here are what we call linearly independent solutions. Linearly independent is just a fancy way of saying neither is a multiple of the other. If that's the case, then these two particular solutions can get combined in a bunch of different ways. But we're going to first verify that these two really are solutions to the system. And so for y1, we can say that the derivative with respect to t of y1, so this matrix right here, cosine t on top, negative sine t on the bottom, that thing must be equal to whatever the coefficient matrix is times this. So coefficient matrix was just 0, 1, negative 1, 0. And if I multiply that by the matrix cosine t, negative sine t, so this side has to equal that side. So a little bit of calculus on the left and a little bit of matrix arithmetic on the right. Now notice this is a 2 by 2 matrix, and this is a 2 by 1 matrix. And we know we can multiply them because that number and that number are the same. So on this side, the derivative of cosine is just negative sine. And in the bottom, the derivative of negative sine is negative cosine. So that side's pretty easy, a little bit of calculus. The question is, do I get the same thing on this side? And I have to do a little matrix multiplication here. So 0 times cosine plus 1 times negative sine, so minus 1 times sine. That's the top element. The bottom element is negative 1 times cosine plus 0 times sine. And so those are pretty easy. The 0 times sine and the 0 times cosine, those go to 0. So we don't have to worry about those at all. And so we just have up top negative sine and on the bottom negative cosine. And what do you know? We have the same thing on both sides, so it checks out. And over here we could do the same thing for y2. And that means taking the derivative of y2, which is sine on top and cosine on bottom. The other side, the question is, does that equal to 0, 1, negative 1, 0 times sine on top and cosine on the bottom? And with a little bit of effort, on the side we have on top cosine, and on the bottom negative sine. And over here, doing the matrix multiplication, you can see we have 0 times sine plus 1 times cosine, so the top is just cosine t. The bottom is negative 1 times sine, so negative sine t plus 0. And so sure enough, that one checks out as well. And so what that tells us is that we have two particular solutions. So on the bottom I'm going to say, so both y1 and y2 are particular solutions. But that means any linear combination of these two is also a particular solution. That means I can say y1 times some constant plus y2 times some other constant is also a solution. And that's going to come in handy on the next page, the very last page of the notes here for this section. So on the next page, it says at the top, the general solution for this system would be constant times that first part plus constant times the second, right? And so we can always find the constant values for these particular solutions, K1 and K2. So for instance, let's presume that we know that the mass spring is initially compressed a distance of 1.5. Initially compressed with a distance of 1.5. So that's telling me that my y of 0 at time 0, I'm compressed a distance of 1.5. So that would be negative 1.5. And the other initial condition that we're given is an initial velocity. And so that right here tells me that the velocity at time 0 is 0.2. So those are my two initial conditions, but we have to kind of translate that into matrix land. And so I'm going to kind of scoot this down a little bit here, or scoot this up a little bit, and kind of put these two together and say we have an initial condition in matrix form that looks like this. Remember, the top is my y, so this would be negative 1.5, and the bottom would be 0.2. And so we have an initial condition, we have a general solution, so that means we have an initial value problem that we can solve. So we need to find the values for K1 and K2. That's what we're going to do. We're going to find the values of K1 and K2 up here that have this as a particular solution. So down below this, I'm going to set up my equation. I'm going to say my y of t, I know the output is negative 1.5 and 0.2. That is y of 0. But that also has to be equal to the right-hand side up here. So that's got to be equal to K1 times cosine of 0 when t equals 0, and negative sine of 0, that first matrix, plus K2 times sine of 0 and cosine of 0. Now, fortunately for us, some of these are really simple, right? Because cosine of 0 is just 1 and sine of 0 is just 0. So really what we have is an equation that looks like this. Negative 1.5 and 0.2. And on this side, it's K1 times the matrix, really simple matrix, 1, 0. And K2 times the matrix, 0, 1. And so without too much work, I think you can probably see that there really are two equations. The top one that says negative 1.5 equals K1 times 1 plus K2 times 0. So K1 is equal to negative 1.5. And the bottom equation is 0.2 equals K1 times 0 plus k2 times 1. So that means k2 is equal to 0.2. And so we can put this together and be able to say the particular solution, y of t, would look like this. K1 is negative 1.5 times its vector, which if you remember was cosine t, and then on the bottom negative sine t, plus k2, which is 0.2, times its vector here, which is sine t, and cosine t. So this thing right here, the way we've got it written, this is in matrix or vector form. This thing is a solution. And not just a solution, it's the solution to the initial value problem. And the good news is that we can just as easily write it in parametric form, right? If we wanted to, we could just as easily say that's equivalent to the system of equations x of t equals the top. So, no, not x of t. What am I doing? Sorry, y of t. This is y of t is negative 1.5 times cosine t plus 0.2 times sine t. And remember, the bottom is not, the top is y and the bottom is v. And so the bottom is v of t equals negative 1.5 times negative sine. So that would be positive 1.5 sine t plus 0.2 cosine t. So this is what we would call scalar or parametric form. Now it's worth noting that this is position and this is velocity, and there's a relationship between those two things that we're familiar with. And sure enough, if you take the derivative of position, that position function, notice that this is exactly what you'd get, the velocity function. Because the derivative of negative 1.5 cosine is positive 1.5 sine. The derivative of 0.2 sine t is 0.2 cosine t. So it's exactly what we would expect it to be if we were in scalar or parametric form. The exact result is what you get when you're doing this in matrix form. Either way, you get the same result, and it's exactly what you'd expect in terms of position and velocity. So this was an example of being able to start with an initial condition and a general solution and come up with a solution to the initial value problem. That gets us to the end of section 3.1.